Welcome everyone. Thank you for coming. My name is Jérôme Nguyen. I'm a PhD student at the Universität der Bundeswehr Munich. I work on FHE and all kinds of other themes in cryptography. And today I will be talking about what kind of security guarantees you may want, you may hope for when talking about FHE schemes. Right. So this presentation is based on a paper we had at Eurogroup with my supervisor, Mark Manulis. And I guess without further ado, we can begin. So I'm not going to re-explain what FHE is, but it is this amazing cryptographic primitive that allows you to compute on encrypted data. It has loads of applications. And since 2009, when Craig Gentry came up with this bootstrapping technique, there have been many papers since then improving on all kinds of aspects of it. Yeah, mainly the research has focused on efficiency improvements and on, roughly speaking, improving the functionalities of FHE schemes. Mostly from a security perspective, the standard was to consider chosen-plaintext attacks. And this was decently reasonable because, FHE used to be totally theoretical and absolutely not practical at all. So like considering like stronger attack models didn't make so much sense anyways, because as long as the primitive is not usable, it's not really important to know if it's secure, this much secure, or a little bit more, a little bit less. It doesn't really matter that much. And the other thing was kind of in the canonical FHE application, which is like outsourced computation. It wasn't so clear if you actually needed anything stronger than this CPA security. And maybe finally, that's more of a personal opinion. FHE seems kind of inherently vulnerable to anything stronger than CPA security, the CPA attacks. And therefore, I think a lot of people weren't actually that interested in looking for anything stronger. But that's a personal opinion. But okay, so maybe I've been talking about it's only being CPA secure, but maybe that's enough, right? Like if it's enough, we don't need to care about anything else. And I would claim no. I would claim no. I'm going to say it's in this strong way, even though it might be arguable that it's application dependent. But let me try to convince you that we really should aim for something a little bit stronger. There have been actual attacks on CPA secure schemes. And one of these attacks was introduced by Li Minchancho in 2021, which is these attacks, these CPA-D attacks on approximate FHE schemes, which were really reasonable practical attacks that totally broke schemes such as CKKS, which is an approximate FHE schemes. There actually have been since then developments, new papers that have shown that this style of attack can also be conducted on exact FHE schemes. So this is a first issue. A second one is the so-called CypherTex validity attacks. One paper that talked about these was by Chilotti and all in 2016. And this is really when you decrypt a ciphertext and you get gibberish back, you might react to it in some particular way, maybe asking whoever sent you the ciphertext what's going on, right? I'm getting gibberish. And this reaction is actually a weakness that can be exploited by an attacker, and then was shown that this actually breaks some FHE schemes. So this is a second thing that we would really like to avoid on our FHE schemes, because it's very common that in FHE we might outsource some computation, and if you decrypt whatever you outsourced and it's gibberish, you might complain to your provider. So it makes total sense that you would do that. But if it leads to a security break, then it could be a big issue. Right, and also there's this thing called func-CPA attacks, which was introduced by Agravel et al. In 2022. And this is about doing outsourced computation, but using the client to help you do some particularly difficult computations, and namely expensive computations such as bootstrapping. And this was actually shown to be also quite effective attacks on some CPA Secure FHE schemes. And okay, so I've listed a few of these attacks. This is actually like not quite exhaustive, but as we see, CPA security might be enough in some application, but it does seem quite finicky. It does seem easy to make mistakes. And actually, when we talk about normal encryption, right, we usually always try to take a stronger security notion than CPA security, exactly because of these kinds of issues, where in some applications it might be fine and in some not. At least, you know, if you have a stronger security notions, it's fine in all applications. And that's kind of what I'm arguing we should aim for. So as I mentioned, for regular encryption schemes, if we're talking about a stronger security notion than CPA security, we will usually always think about something called chosen-ciphertext attack security, so CCA2. And so this is a classic indistinguishability game where an adversary gets access to the public key and a decryption oracle, meaning that if he's allowed to ask for decryption of any ciphertext of their choosing. And then the adversary is going to choose two messages. The messages are going to be, one of the messages is going to be encrypted, and the adversary needs to decide which of the two ciphertexts has been encrypted. And so in this attack model, the adversary also gets a decryption oracle after receiving the challenge ciphertext, right? But obviously it's not allowed to ask for the decryption of a challenge ciphertext at that point because it would win trivially, right? So this is kind of a gold standard of security notions when we talk about encryption. But unfortunately, it's quite well known that this is not possible for FHE schemes or homomorphic schemes in general, exactly because they are homomorphic and the attack is really easy to see. So if you have a child ciphertext, you can just re-randomize it by adding, for example, an encryption of 0 on it. And then the ciphertext will look different. It will be the C prime, right, which looks different from the C star. And therefore, I'm allowed to decrypt it. But since I only homomorphically added 0, the message doesn't change, and I get back the challenge plain text, and I win the game trivially. So this is kind of disappointing, obviously. But this is not the only security notion. Another one is called CCA1, which is a weakening of this CCA2 notion, where the adversary does not get the decryption oracle anymore after having received the challenge ciphertext. And so, okay, so this means that the previous issue of it we've seen doesn't exist anymore. So this is already quite nice. And actually, there are some results that do say that it's possible to build CCA1 secure FHE, but the results that existed were only for either leveled FHE schemes. So by that I mean schemes that only are able to evaluate a bounded number of bounded depth, a circuit with a bounded multiplicative depth. And also maybe for there were some construction for general FHE, and by general FHE I mean FHE schemes that do not use bootstrapping. But since we don't know any actual FHE schemes that are in any way both efficient and do not use bootstrapping, this was kind of a somewhat empty result. And there's this folklore result that says that if you do use bootstrapping in your scheme, then you can't be CCA1 secure. And this comes from the fact that when you use bootstrapping, you release what's called a bootstrapping key to the public. And that bootstrapping key is essentially an encryption of a secret key. And the issue is, since we have an encryption oracle, we can always ask for the decryption of the bootstrapping key and get back the secret key, which obviously means that you broke the scheme. Okay, so this is kind of a landscape of the security of FHE schemes. And the question is really, can you find something here where we are between this impossible for FHE CCA2 security notion and this somewhat weaker CCA1 security notion? And in particular, can you do that while not modifying the requirements for your FHE schemes? And by that, I mean, can you do it while still bootstrapping, which is really the only way we know how to do FHE in any good, efficient way. To answer that, I'm going to give a little bit more intuition about the CCA security notions. So CCA1 security, if we go away a little bit from the formal definition in the game, and we really think intuitively what we want out of it, it means that essentially, if you see a decryption of any ciphertext, it should give you no information on the secret key, loosely speaking, right? So that means that if you are able to somehow get to my desk, do a few decryptions, but you don't actually see the secret key, well, you don't know anything more about the secret key than what you knew beforehand. So that's kind of morally what CCA1 is saying. And CCA2 is a little bit stronger in a sense, or quite a bit stronger maybe, because apart from this non-malleability that's kind of well known about it, what it also says, loosely speaking, is that if you decrypt a ciphertext, it should give you no information on the decryption of another ciphertext, which are all like kind of intuitive things that you really want out of it, right? It's if you have like an encryption scheme and you decrypt some stuff, then you obviously know that information, but it should give you no more information than that, right? And if we look a little bit closer at CCA2 security, so we have this thing where okay, you decrypt something, you decrypt this C, it doesn't give you any information on the C prime. But what if we relax this requirement slightly, a little bit, and we say, okay, we kind of maintain that, but we add a condition. It gives you no information on another ciphertext if you don't know the relation, the homomorphic relation between C and C prime. And by that, I mean, you don't know if C prime has been obtained through homomorphic addition of some C or multiplication or stuff of that nature. And this seems quite reasonable in a sense because CCA2 security kind of already has this condition implicitly, but the thing is, it's always true because the way CCA2 is defined means that you cannot know the relation between C and C prime. And in this relaxation, we're allowing the possibility that someone would know the relation between C and C prime, but we're saying that as long as they don't know it, then you don't get any additional information by decrypting. right? And using this intuition, we defined a new security notion, which we call IND-CCA for indistinguishability against verified chosen-ciphertext attack. And okay, I'm going to show you a little bit that it is indeed strictly between this CCA1 notion and the CCA2 notion. At the time where we came out with the paper, it was the strongest known achievable notions for FHE. Since then, there has been a slight extension, but I'm not going to talk about it today. And okay, there's an equivalent formulation in the non-malleability kind of paradigm, if you're familiar with that. But I'm also not going to talk about that. If you're interested in that, I'd recommend opening the paper. And okay, maybe what's really interesting about it, because you can really define anything you want, is that this is actually achievable in the random oracle model, and it allows for schemes that use bootstrapping. So this means that you can use your favorite FHE scheme, namely, I don't know, BGV, TFHE, GSW, whatever you like. It's fine. Right, and to do that, we're going to use also a snark, but I'm going to talk more about this in a bit. First, how do we define this? So the main issue when you have CCA2 security for FHE is that when you do a homomorphic evaluations and you obtain some kind of evaluated ciphertext, well, there's no way of knowing how this ciphertext you had was obtained, right? Once you see hat, that's it. You're stuck, right? And so if we think about the decryption oracle we had earlier in the CCA2 game and this condition that you're not allowed to decrypt the challenge ciphertext, well, there's no way of checking kind of more than that, checking if it's related to the challenge ciphertext, and not only if it's equal, right? So the idea was very naively, maybe, what if you could? What if you could know where a ciphertext comes from? So if we kind of define an algorithm called extract, which is loosely speaking inverses the evaluation algorithm, meaning that if I put C hat in it, I get F, and the input ciphertext that I had for my homomorphic evaluation. And I kind of add these further requirements that the ciphertexts are fresh encryptions, meaning that they have just been output by the encryption algorithm, and they haven't gone through the evaluation algorithm at all. And that the extraction algorithm kind of does what you expect, meaning that it, loosely speaking, behaves like an inversion, meaning that if I decrypt C hat, I get the same thing as if I apply F on the decryption of C1CL. Then we actually have all we need to define this vCCA notion already. How do we do this? We're going to define a new decryption oracle. And this decryption oracle is first going to extract the ciphertext that you asked it to decrypt. And it's going to know from where this ciphertext has been obtained, so through which kind of homomorphic evaluation and through which input ciphertext. And if the challenge ciphertext is not among the input ciphertext, then it will decrypt. And we can plug this in a normal indistinguishability game. It looks exactly like the CCA2 game we had earlier. Apart from that, in the second phase, in the second decryption phase, the decryption oracle is replaced now by this vCCA oracle that only decrypts if a ciphertext is not related to homomorphism to the challenge ciphertext. Then then we can show that this is a security notion that kind of implies everything we want. So as promised, it is obviously weaker than CCA2. That was kind of always going to be the case, but it is strictly stronger than CCA1 security. it implies kind of what we talked about earlier, this chosen verification attack notion, and it applies this func CPA notion too. On this graphic, there's also this an IND-CCA notion, which I'm not going to explain either, but it's related notion for homomorphic encryption that is only over a single ciphertext and not multiple ones. And yes, so this vCCA notion is it kind of encompasses every attack we know of on FHE schemes in a somewhat similar way to how CCA2 security encompasses all the attacks that we kind of care about for regular encryption schemes. So this is very nice, but is it possible to build something that is vCCA secure? And yes, we can. And we have a generic transformation that allows us to transform any FHE scheme that is CPA secure into an FHE scheme that is vCCA secure. So this happens in 2 steps. First, we're going to do what we call embedding an FHE scheme in a CCA2 secure encryption scheme. So what do I mean by this? So we're going to break the homomorphism in a particular way. So here, this is abuse of notation, but by this CCA2 of M, I mean that CCA2 of M is an encryption for a CCA2 secure encryption scheme of a message M. And we want it to have a particular form. We want it to be a tuple of 2 elements. On one hand, we have this C prime, that is the normal homomorphic encryption of M. And T is some kind of additional information that makes it CCA2 secure. So this is probably going to be more clear if I give a few examples. So what you could do, for example, if you're considering symmetric FHE schemes, is use encrypt then MAC, where you use a MAC scheme to tag the C prime, which is the homomorphic encryption. And it is very well known that when you do that and you say that the ciphertext is now both, this is CCA2 secure. And as you can see, we have this particular structure that I was asking, that I was requiring, where you have on one hand the homomorphic encryption, which is unchanged with C prime. And on the other hand, you have this additional information that makes it CCA2 secure. So this also works actually with encrypt and sign for the same reasons. And asymmetrically, what you could use, for example, is the Nguyen double encryption, where you encrypt the same message twice, and then you prove that with a NISIC that you encrypted the same message twice. And yeah, this also has a structure that we want, right? Because you encrypted the message with your homomorphic encryption, so that's there. And then you've got like C2 and the proof, that's like kind of additional information. What you cannot use, for example, is Fujisaki Okamoto, because while it is CCA2 secure, it doesn't have the structure that we need. Okay, so that's the first step. The second step is then, oh yeah, pardon me. First, I did say that we could support schemes that use bootstrapping, and to do that, essentially, we need to make sure that the bootstrapping key is not a valid ciphertext for the CPA2 secure encryption scheme, which makes sense, right? Because we don't want the decryption algorithm to allow the bootstrapping key. We wanted to return some kind of error message. Right, so if you have a bootstrapping key BK, we release BK as is. Very importantly, we do not release the CCA2 version of it, right? It needs to remain an invalid ciphertext for the CCA2 encryption scheme. All right. Okay, so now on to the second step of the transformation, and this is where we use SNARK, so a succinct non-interactive argument of knowledge. And we're essentially going to do two things. First, we're going to prove that we know the CCA2 ciphertext that we use, that we want to use as input ciphertext. So that means that if you want to use T1 prime CL primes as input ciphertext, we're essentially going to prove that we know T1 TL. And on the and afterwards, we're also going to prove that the evaluated ciphertext C hat has been obtained through the correct use of the evaluation algorithm with these ciphertexts for which we know the CCA2 kind of counterparts, right? And for that, for technical reasons, we need actually quite strong snarks, where we need them to be non-rewinding, simulation extractable, and black box extractable. So these are security notions for snarks that I'm not going to explain. These are slightly non-standard, but these snarks do exist in the random oracle model, and therefore we can use them for the construction. And so if we bring everything together, what did we really do? So if you look kind of as the kind of normal workflow of homomorphic encryption, evaluation, and decryption, you first encrypt some messages, you get ciphertext, you evaluate them with some function to obtain the C hat, the evaluated ciphertext, and then someone decrypts and hopefully obtains F of the original messages. And an adversary really has multiple places where they can interfere. The first thing is they could mess with the input ciphertext to obtain some kind of attack vector. And for that, we introduced this embedding step that we had in the beginning, the first step. And okay, so if you can't mess with the input ciphertext because you have this embedding step, what else can you do? Well, you can actually mess with the evaluated ciphertext, because nothing links right now the C hat, the evaluated ciphertext, to the input ciphertext. So in essence, this C hat could come from somewhere totally different right now. And this is also something that you can use to do attacks. And so that's why we introduced this thing with the snark, where you prove the relation of C hat to this input ciphertext. And the relation is exactly the correct use of the evaluation algorithm. And when we do both, this is actually then vCCA secure. So yeah, we were able to show that. And that's it for me. As a kind of summary, so we have introduced this new vCCA security notion, which is achievable through generic transformations in the random oracle model. It was, at the time of publishing, the strongest achievable security notion for FHE schemes. And maybe most excitingly, you can use any of your favorite FHE schemes because it is compatible with bootstrapping. Right. Thank you for your attention. I'd be very happy to answer any questions or if you have any remarks.